Okay, so we had that function that I shouldn't start with an integral, but let me just copy what we had. What was it? Our function was, did I choose 0? Yeah, I chose 0 to 2. So as a continuation from last time, so I had f of x was x squared plus 1. And we determined that the exact area under the graph of this function between 0 and 2, and we determined it with the limit of the Riemann sum. So the exact area was the limit as n approaches infinity, the number of subintervals from the sum from I equals 1 through n subintervals, and they go to infinity, from delta x f of xi. Delta x is a constant. It does not depend on I, but this xi moves from spot to spot. So f of xi, f depends on, x depends on I. So we got that this was 14/3. So we determined that step by step. It took us a while because it was the first example and I needed to explain. But we used the limit of the Riemann sum. And we determined that exactly. We had with the leftmost point and rightmost point and the midpoint other numbers. And 14/3 is the exact. Okay. So now I will introduce basically two new symbols. The first one is called the indefinite integral. And what is the indefinite integral? When we looked at section 4.9, we said, if I'm given f prime, I can find f of x. And I can find basically the most general antiderivative, putting a constant c. What does this mean again? All these functions have the same derivative. And now, what is this indefinite integral giving us? Exactly this. So this is the same thing with the s, right? The sum, but it's a stretched s from f of x dx. And the answer is, if I'm given f of x, remember the second notation? I mentioned those last time. Let me mention again. So if I'm given f of x, then I will determine the uppercase f of x plus a constant c. And again, you can say, what's the big deal? Well, the big deal is that if this is given to us as a function, because even the derivative is a function, we are going to use the uppercase f for the antiderivative plus a constant c. So uppercase f plus a constant c. And this is the indefinite integral. It's the sum base times height plus base times height plus base times height, but in the form of a function, or I would say a family of functions. Why is it a family of functions? Because if c is 5, I have one function. If c is negative 3.2, I have another function. If c is 0, I have another function. And I can go on forever. So that's why this is a family of functions, or the most general antiderivative. So what do we know about the indefinite integral? The indefinite integral basically goes with the first section that we studied after test 3. That gives us, so it's the indefinite integral from f of x dx. Let me just make one remark before I continue. There is no integral without dx and some function, even if it's 1. It has to be something in here. So the indefinite integral, it's a sum. It's the sum of all areas f of x dx. Base times height plus base times height, they're all the same with the limit of the Riemann sum. So if you want these two represent this, and f of x is here and delta x is dx. If you want to think in those terms. It's not exactly the same because I'm still talking about the indefinite integral. I haven't gotten to that yet, the detailed one, which is the definite integral. Okay, so the indefinite integral from f of x dx is the most general antiderivative plus a constant c. This is a family of functions, infinitely many, because c can be anything. Infinitely many functions. Or you can say this is the most general antiderivative of this function. There is a huge benefit here. How do I check? How do I check that I determine this correctly? I can differentiate both sides. And I'm going to discuss this today. But I want to put it here so we have it. The uppercase f of x plus c prime has to give us the function. And I will explain why today. So we have a way of checking the answer of any indefinite integral. I differentiate the answer, whatever I get, and I have to get this function that I was given initially. If these two are okay, then this is correct. So this was a little introduction on indefinite integrals. Now the second one here, see next page, okay, for that one. So now we're going to talk about the definite integral. Okay. Stop me if you have questions, please. So the second one is the definite. The definite integral is still a sum, but from a to b, it's definite. I'm told the limits of integration. So a and b are limits of integration. Nothing to do with LIM. It's the lower number and the upper number called limits of integration, of course, of f of x dx. However, the answer is a number. And the answer is not a function. The answer is always a number. So then, and this is the exact area or the limit of the Riemann sum. So now the exact area is the integral from a to b from f of x dx. What exact area? Under f of x between a and b, which is the same with the limit as n approaches infinity from the sum from I equals 1 through n from f of x I delta x. This is the exact area. We already know from section 4.9, although we did not use the symbol, we only determined functions, we already know how to determine an indefinite integral. The question is, how do I determine the definite integral? So the definite integral is a number. How can I check? I cannot. I could just plug in the graphing calculator and determine this number to make sure I didn't make an error. But I don't have any other technique of finding or checking this answer. Okay. So before we learn how we evaluate these definite integrals, let's look at some properties. And this is basically where 5.3 starts. So let's start with properties of the definite integral. The definite integral has several properties that we need to look at. So imagine again that this is our function f of x. Here is, of course, our favorite interval, a comma b. And this is nothing else but the definite integral from a to b from f of x dx, or the exact area. No approximations whatsoever. So here's our first property of the definite integral. What do you think the integral from a to a from f of x dx will be? A wild guess.
0.
Absolutely, there is no area between a and a. Awesome. Good. Moving on to the next property. Number 2. You're gonna like this one. It's the same with two other properties that we looked at. F of x plus g of x dx. And of course, if I have minus here, what do you think is a wild guess? We had the same property for limits. We had the same property for differentiation. So this is exactly the same thing. And we had the same property for the summation notation. Anyone? No one wants to give it a shot.
Would it be the integral of f of x plus the integral of g of x?
Very good. From a to b, very good. Plus the integral from a to b from g of x dx. And of course, if there is minus here, it will be minus here. Good. Awesome. What do you think about number 3? The integral from a to b from a constant times f of x dx. What do you think about that? We had the same properties with limits, the same properties with derivatives, the same properties with the summation notation, the same property with integrals. What do you think?
Constant times the integral.
Very good. Of course. Number 4, the integral from a to b from a constant dx. Of course, the constant comes outside like here, but then I have 1. I have to have something, even if I don't write it. So now, what function prime is 1? Or, let's take a look. Here is the constant c. Any constant you want. Here's a and b. Can anyone give us this area without even thinking in terms of integrals? So if you can give me the area, I'll put it there. I have the height and I have the base. So what would the area be?
A times B.
But this is b minus a, right?
Wait, no, the height times b minus a, I mean.
Correct. Very good. C times b minus a. Or another way, which we will learn today, is x from a to b times c. But let's leave that for maybe half an hour from now. Okay, another property. So let's take a look at this function now. I want to determine the integral from a to b from f of x dx, which is this area. But I can determine it by adding this area to this area. How will I write it? The integral from a to c from f of x dx plus the integral from c to b from f of x dx. So I can determine the area, and has as many pieces as I need. It doesn't matter, as long as I fill it in completely. So the integral from a to b can be the integral from a to d plus the integral from d to c plus the integral from c to whatever plus the integral from whatever to b. I can split it in as many integrals as I need, or as many areas. And this is very useful, and you'll see when. Here's an example. Let's say I have a piecewise defined function that looks like this. This is one piece, one function, and this is a different function. So the integral from a to b has to be split right in the middle, or wherever this is. And I have to determine this area from one function and this area from a different function. So this is extremely useful, an extremely useful property. Is this okay? Any questions? Okay, one other property here. We're going to apply all these in a minute. We're going to choose problems. 6. The integral from a to b from f of x dx is the opposite of the integral from f of x dx with the limits reversed. And why is that? It's because if the here dx, or if you want normally delta x, is b minus a over n, but here delta x is a minus b over n. So this here is the opposite of this. That's why this minus pops up if I reverse the limits of integration. So if I say the integral from 1 to 5, then it's the opposite of the integral from 5 to 1, because this will be negative. So this negative with this negative will give us positive again. Any questions? Okay. Now 7. Odd, even, both on symmetric interval. On a symmetric interval. What does a symmetric interval mean? So let's take a look at an odd function. Our very nice example for an odd function is x cubed. So this is an odd function. What about the symmetric interval? Like between -4 and +4, between -a and +a. This is a positive area. This is a negative area. What do you think the integral from this odd function from negative a to a from f of x dx will equal to? You don't have to say anything just now. Let me do the same thing for even. Our nice example for an even function is x squared. So now, again, the same thing between negative a and a. Both are positive areas. So the integral from negative a to a from f of x dx. One very important remark here. f of x must be a continuous function on whatever, a comma b, negative a, whatever the interval is. Okay. So now let's analyze these two. This is a very important property. If I know that the function is odd, of course continuous on the interval, and odd, and I see the symmetric interval, negative 3, 3, negative 10, 10, negative pi, pi, what will the answer be?